Actually, Wolfgang Hilber is an assistant professor in my group, and as mentioned, he had to cancel his trip in the last minute. So I'm stepping in for him. The presentation is about a technology that can be used to create magnetic actuation in microfluidic circuits. And Wolfgang worked on the technology and devised a device to demonstrate the feasibility of this method. Here's an outline of the talk. I'll start with brief motivation, which addresses some issues that you commonly encounter, and then propose a solution concept, show a device concept for the demonstrator device, which is intended to show the feasibility of this technology, discuss the working principle, a few words on the fabrication technology, and I'll show some experimental results with the prototype device and finish with conclusions and an outlook. So the motivation is that magnetic actuation on the macroscopic scale is a very attractive means of creating actuators. In microsystems, the problem also is that it's very difficult to get the magnetic field focused in the area where you actually want to have it. In a lot of applications, this doesn't matter because it just puts the entire chip in the field, but often you want to modulate the field and so forth. And so, in other words, what you commonly encounter is that it's very difficult to obtain a good spatial definition or resolution of the magnetic field on your chip or on your device. Furthermore, for the same reason, it's very difficult to achieve high flux densities, and often the technologies that you need to use are very complex. They are hybrid technologies. So the solution concept that is proposed by Wolfgang in his work is to use PDMS as a base material for the microfluidic system, and this is kind of doped with neodymium powder to create a magnetic guide, so a magnetic circuit. This technology turns out to be very feasible and easily controllable and without cost-intensive equipment, and it has several advantages. For example, for the realization of microfluidic components. As application to demonstrate the feasibility, Wolfgang selected a device where a ferromagnetic solid, a ball or a sphere, is actuated in a microfluidic chamber to create a ball. So the neodymium powder that is embedded in the PDMS magnetic circuit is used in the form of a powder where the typical grain size is 1 micron. So the device that is selected to demonstrate this technology basically consists of a microfluidic chamber with several microfluidic inlets and outlets. These channels will be realized also in PDMS technology. This is a very established thing, so you create a channel and then you have a top layer and you fuse them. And the idea is in parts of the chamber where you don't have the microfluidic channel to have kind of a magnetic guide. So this would be only the magnetic guide. So the gray area is a region with very high permeability where you guide the magnetic flux that is excited by external standard coils. They are also small, but you don't need a special technology. These are common hand-wound coils that I will show later on. And if you create a guide such that you have a tapered geometry, you can enhance the flux density in order to have a high magnetic field inside this chamber. And depending on what particular waveguide, magnetic guide is excited, you can move the ball in this chamber and close or partially close microfluidic channels, and in that way direct your microfluidic flow. You see this better in this picture. So this is a top view where the top layer has been removed to make it more visible. So what you see here is the ball, the ferromagnetic sphere. So the area, the chamber has dimensions of millimeters. The dark areas are the parts of the PDMS that is loaded with this neodymium powder, and the light areas are standard PDMS structures, and here you also see the channels. So you have 4 channels, one here, one here, one here, one here, and in this case the sphere is actuated in such a way that you, for example, these are the magnetic guides. If you actuate the coil that is connected to this guide and the one that is connected to this guide in a proper manner, you may create magnetic flux along this line. Here you see a FEM simulation of this, and the ball will be will move in this corner, will move in this part of the chamber and block this inlet. If you only actuate one of the guides, then it will move here and will partially block, for example, this channel and this channel. You can play with the fluxes or with the coils of the other 3 guides. You can either not actuate them, then the flux will be distributed. You can partially excite this one and so forth and play with the dynamics. But from the concept, just that the ball is moved in this chamber. And here you see, before I show the performance and what states you can achieve, with this device you can basically create some simple kind of microfluidic logic switch. If you want, before I discuss this, I think we say something about the fabrication technology. So this technology was not invented by Wolfgang. In 2001, there was already a report on magnetically modified elastomeric material in this reference here. Specific to this approach here is that the composite material, as mentioned before, PDMS, with a heavy loading of neodymium powder, so you have a weight ratio of 8:1, is used. The powder is of that type. Regarding the powder, you would need one that is soft magnetic. This one is not so soft magnetic, but it was the one that was available at the time, so you will have some remanent effects here, but there's also neodymium powder with smaller hysteresis. So the wave guiding, the guiding of the magnetic field also works very well. So this PDMS was used, and the prototype was realized by creating the PDMS parts that are not loaded with the powder separately from the guides, and they are later fused by means of an additive process, which works very well for PDMS. And for the microfluidic parts, the standard method is used, that is used for microfluidic channel a lid on top of the channel, and then you have the microfluidic channel. So here are the inlets of the microfluidic channels, and here you have the, if you want, the magnetic contact pads of these 4 guides. So in the experiment, what Wolfgang did was he selected one of the channels, say number 1, so this is 1, 2, 3, 4, as the inlet, and measured the flow that came out of the other channels, and the flow was generated by a silent pump that was connected to channel 1. And here you see the states that you can achieve by actuating the magnetic coils that are put on top of this. So here you see, so these are 4 common hand-bound coils, so they don't need to be that small because the magnetic flux is then later conducted by this guiding structure to the center of the device. So they look like this. You put them on top, they hit the other side of the coils. They are connected by a material of high vulnerability to closeness in order to have high flux density. What you can do now is you can realize 9 states. If you don't actuate anything, the ball will be in the center. If you actuate, so here you don't see the magnetic guides, but if you actuate these 2 here, the ball will block channel 1. In this case, channel 2, channel 3, channel 4, but you also can partially block 2 of the channels. Here, for example, channel 1 and 4, and so forth. And the experiments show exactly what you would expect from such a device. If you, what you see here is the axis here is the input flow, everything stays to the input flow, so this is 1. And the other symbols here show the flow at the other ports, fluidic ports. So for example, if you block the input flow completely, then the other flows are not measurable. If you have it in the center, they are of equal size, 1/3 as it should be, each of them. If you block outlet number 2, the flow is distributed into 4 and 3, where the flow into 4 is somewhat higher, because this is partially blocked by the 3. It's exactly to the expectations. The reverse case would be that you block the opposite, and these two fit to each other. Here you have to flow in 3 and 2. Then the hybrid logical states, if you want, are these where you partially block 2 channels. Here, for example, the inlet channel is partially blocked and the outlet channel number 4 is partially blocked. And you see, as you expect, that 4 will not get as much flow as the other 2, and they are also not equal. 2 is closer to 1, so for 2 you have a higher flow, and so forth. Otherwise, you see that the structure is fairly balanced regarding symmetry, so you have approximately the same flow fractions in all directions. So with this you could create a simple microfluidic model. But the main intention of this work was to demonstrate that this 3DMS technology can be used to concentrate magnetic fluxes. So in conclusion, it has been demonstrated that 3-dimensional composite structures in PDMS can be realized and used to guide magnetic flux densities in microstructures, for example, in microfluidic circuits. The pilot device shows microfluidic switch or a valve, if you want, that can, for example, be used to do microfluidic logic operations. And the goal is to work further on this approach and devise other magnetically actuated mini microfluidic